as I've told in one of my previous lectures, that there are various kinds of standards available all over the world, but generally two standards are usually followed on the majority of the part of the world. First one is the IEEE standard that is being followed usually in USA, and other one is the IEC. That IEC is being followed in European countries as well as in India also. In most of the projects IEC is being followed. Okay, so let us see what are the classifications of current transformer according to IEC as well as IEEE. Now the latest IEC for the classification of current transformers is IEC 61869 part 2. Earlier it was 60044. Okay. Now, according to IEC, the current transformers are being classified according to their use. And the accuracy limits, okay, or the maximum possible errors. Now we have various classification like 0.1, 0.2, 0.2s, 0.5, 0.5s, 3, 5.0. Okay, now usually these kind of classifications are for some kind of metering or instrumentation purpose. The CTs which are being used for the protection purpose have a letter P. Usually they have a letter P in their classification. Okay, so we have a classification like 5P, 10P. Now there are various CTs which also have classification PX and PR. These CTs are being usually used for the overcurrent protection, and PX class are being used for unit protection like differential protection. And these CTs have a special effect called anti-remanence, that is, the remanence will be less than 10% in any case. These are designed in such a way. Okay, so wherever we have a requirement that there should not be any remanence in the CT, then we call for CTs classified by PR. Okay, this P represents protection class. This PX represents that it is being used in protection only, but X means that all the characteristics of the CT will be determined using the excitation characteristics. Although excitation characteristics are used in every kind of CTs, but here the specification will directly come out of excitation characteristics of the CT. Usually we define or we ask for the knee voltage, the CT secondary resistance, RCT, okay, and the current. These three parameters are defined for this class of CT. Now let us deal with first 0.1, 0.2, 0.2s, 0.5, 0.5s and others. Okay, now this S means special class. These are utilized for revenue metering, okay, precision metering, okay, and in compared to 0.2 and 0.2s, 0.2s is more accurate at various levels of current, okay, that we will see when I will write various characteristics here from the table. But this 0.2s is more accurate compared to 0.2 at lower value of currents. Okay, so usually the electricity authority regulations, CEA regulations, call for 0.2s cities for metering purpose, for the revenue metering purpose. Okay, for backup metering purpose we usually go for 0.5s. Okay, now let us see what are the criteria or what are the characteristics of these kind of cities. Usually these cities are being used for 25% to 100% of the rated VA capacity of the city. Let us say the city is having a rated capacity of 100 volt ampere burden. IEC usually shows burden in VA and IEEE usually shows burden in the ohms. Okay, so let us say the city is rated for 100 VA, then we can utilize these metering cities for the normal currents ranging from 25% to 100% of the rating of the burden. The readings will be quite accurate. Okay, similarly all these cities, metering cities, will be applicable for 25% to 100%. Same. However, this 3.0 and 5.0 will be giving good results only between 50 to 100% of the rated VA connected across them. Okay, now all the protection class cities will give good results over 100% of the rated VA connected to them until the accuracy limiting current, which is equal to accuracy limiting factor into normal current. Okay, or the nominal current or the rated current. That these two terms we have seen in our previous lecture. Similarly, this will give good results up from 100% to ALF into IN. Okay, now let us see their characteristics. This 0.1 class CT will give a ratio error. This is ratio error in percent. This is phase error in minutes. It is easily available in the IEC. Okay, no need to remember. Now ratio error will be 0.4%, 0.2%, 0.1%, 0.1%. This 0.4 will be at 5% of the rated value of the current on the secondary side. This will be for the 20% on the secondary side. This will be 50% and 100%. Okay, so you see that if the current is lower than the threshold, then even then the CT will be having higher error. Okay, that's why this 25% to 100% has come. Also for 120% it will be having 0.1 only. For normal overloads usually we take 20% overload. Okay, now similarly for 0.2 class CT, 5%, 20%, 100% and 120% rated load, the error will be the guaranteed error, that is error will be less than the guaranteed one on these currents will be 0.75%, 0.35%, 0.2% and 0.2%. Okay, for the 0.2 special class the error will be little lower. At 5% it will be 0.35, at 20% it will be 0.2, at 100% it will be 0.2 and 120% also it will be 0.2. So in this way we can see that 0.2s is comparatively more accurate than 0.2. Similarly for 0.5s the error will be 0.5% at 100%, 20% and 120% for 0.5s. In this way we can find the table in the IEC and we can find the specification for the ratio error and the phase angle error. The phase angle error will be 15 minutes, 8 minutes, 5 minutes, 5 minutes for these value of currents. Okay, so in this way we can find the ratio error and the phase error of a CT at a given current for a one kind of or the various kinds of classification of the CTs. Okay, so this is the classification. Now usually we will find that sorry, a city is classified as 5P20. What does it mean? This 5P is the classification which I am showing here, and 20 is the accuracy limiting factor, ALF. That is, it will be having guaranteed error up to 20 times of the rated current. Okay, so this 5P20 is showing this thing. So 5P, the error will be 5% for these values. Similarly, for 10P, the error will be 3% and 10% at 100% and ALF into IN. It is 1%, I think. Here 1% and 5%. So there are various kinds of values of error for various kinds of levels of current for each kind of CT. However, the nomenclature is this: the class of CT and the accuracy limiting factor, and this P represents the protection. That is, the CT will be used for protection purposes instead of metering purposes. Metering purposes we use these kind of CTs. Okay. Now for PX we classify, we ask for the knee voltage, RCT and the I current. Similarly, PR is again a special CT which is having anti-remanence factor. Okay. Now according to the IEC, there is a special definition of the knee point voltage. Okay, what is that? We know that the excitation characteristic of the magnetic material or the CT is like this. Okay, so the knee voltage according to IEC is that voltage that when I increase this voltage by 10%, my current will increase no more than 50%. So this point will be the knee voltage. That is, for 10% increase in the voltage, the current will increase no more than 50%. This is the definition of knee voltage as per IEC. As per IEEE, what we do? We plot the excitation characteristics on log scale. Okay, at the point where this curve is having a gradient of 45 degree is known as the knee point. Okay, so wherever the curve when plotted, this curve when plotted on the log graph has a gradient of 45 degree, that point is known as knee voltage according to IEEE. But there is a difference between these two definitions, and the difference comes out to be around 1.5 to 10%. Okay, so in this way we can see that these two standards classify the knee voltage differently, and the difference is around 5 to 10% between the definition of these two knee voltages in these two standards. Now we have seen how to classify the CTs according to IEC. Now in the next slide we will see how to classify the CTs according to IEEE. The relevant IEEE is C57.13. Okay, then similarly in IEEE also we have metering class 0.1, 0.3 like that. Okay, 0.2s also special class, but in the protection part the nomenclature is little different in the IEEE. Similarly, this 0.1, 0.3 is having different criteria in IEEE. So we should refer IEEE to find the various ratio and the phase errors for the metering CTs. For the protection cities, I will show how to utilize or understand the nomenclature according to IEEE also. That I will do in the next slide by erasing this. The IEEE assumes an accuracy limiting factor of 20. That is, normally it is assumed that ALF will be 20 and the rated secondary current is 5 ampere in IEEE and 1 ampere usually in IEC. Okay, this is the difference. So the secondary current will be 100 amperes at accuracy limiting value. Okay, now the nomenclature in IEEE is very easy. It is having two sets of integers divided by one letter. This letter will either be C or T, like 10C 400, 10T 400. So we don't need to bother about C and T. C means that the various characteristics of CTs are fixed and these are given by the manufacturer. T means that there is some uncertainty in various characteristics of the CTs. So to determine the various characteristics, we should do test on the CT to find all those values. Usually we find C common in the market. Okay, this is not that common in the market. So now what is the meaning of 10C 400 or something else? It means that at the maximum current, the error will be 10% and the voltage generated on the secondary terminals will be 400 volt. Okay, so the classification of CTs in IEEE is very easy. So let us solve a numerical example to understand this concept of nomenclature of CTs according to IEEE. Let us see that numerical example in the next slide. Now let us see the numerical example. Here we are asked to find the nearest equivalent CT class in IEC for 10C800 CT of IEEE classification. Now this 10C800 is also known as B8. B means burden and 8 means ohm. Now we can see that at 20 times of normal current, the voltage generated on the terminals of CT will be 800 volt. So burden connected will be simply approximately 8 ohm. So that's why this has come here. Okay. Now this CT is going to have 10% error at this current, 100 ampere current. Okay. Or the 20 times of the ALF. ALF is 20 times. Error is 10% and this burden is 8 ohm. Now we want to find the value of burden in volt amperes. So value of burden in volt ampere will be, rated burden will be 5 ampere secondary current I squared into 8 ohm. So the rated value of the burden is in VA is simply 200 VA. So the nearest possible CT in IEC equivalent nomenclature will be a CT having 10% error with a accuracy limiting factor of 20. Okay, so 10p20 and its rated VA burden will be 200 VA. Okay, so in this way we can find equivalence between the two CTs. This equivalence is not 100% exact because of difference in the classification of the knee voltage in IEEE and IEC. Okay, now there is a formula which we usually use. The knee voltage according to this IEEE is equal to the knee voltage in IEC minus normal current into accuracy limiting factor into RCT divided by 1.05. This 1.05 factor is that 5% difference in the definition of the knee voltages. Okay. Now from this we can see that there is a little bit difference in the definition of terminal voltages also in IEC and IEEE. IEEE gives the voltage at the terminals of the CT. That is, it includes the drop in the winding resistance and the leakage reactance. However, IEC gives this value according to the induced voltage in the CT. That is, this cannot be actually measured because there will always be a current flow whenever we connect any meter, but terminal voltage can be measured. Okay, so IEEE and IEC are having this difference also, that IEEE is always give the terminal voltages, IEC gives the induced voltages. Okay, that's why I have subtracted the value of the drop in the resistance of the CT secondary, okay, at the maximum value of the current when saturation will be there. So in this way we calculate the knee voltage in IEC and IEEE. Usually this will not be asked in GATE, but this lecture has been made for the professionals or the engineers who are dealing with design of CTs. Okay, so if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.